Complex numbers are usually taught as a trick for solving equations. But there's something stranger they're secretly for. And following that question leads all the way into 3 dimensions, to a strange 4-dimensional number Hamilton spent a decade fighting for. Multiplying a complex number by e to the I theta rotates it, by angle theta, around the origin, and it doesn't change how far it is from the origin. If z equals x plus y is a point in the plane, then z times e to the I theta is just z, rotated counterclockwise by theta. That's the whole trick. Rotation, a geometric thing, something you'd normally reach for a protractor to do, becomes ordinary multiplication. Here's why. Any complex number can be written in polar form. Z equals or times e to the I phi, where r is the distance from the origin and phi is the angle. When you multiply 2 complex numbers in this form, their magnitudes multiply and their angles just add. So multiplying by e to the I theta, which has magnitude 1, leaves the length completely unchanged and adds theta to the angle. That's rotation, mechanically, not just by definition. Let's make this concrete. Multiplying by I rotates a point 90 degrees. Check. I equals e to the I pi over 2. Take z equals 1, the point 1, 0. I times 1 is I, the point 0, 1. Rotated 90 degrees counterclockwise. I times I is negative 1, the point dash 1, 0. Another 90 degrees. 180 total. This is why I squared equals negative 1 makes geometric sense. 2 90-degree rotations equal a 180-degree flip. One more piece, and it's worth actually deriving, because we'll need the identical logic later for real-flight computers. E to the I omega t, rotating with angular velocity omega, is this rotation operator applied continuously. The point 1, 0 multiplied by e to the I omega t at every instant, tracing out the unit circle. Now, why does differentiating e to the I omega t give you I omega times e to the I omega t? Let's not just quote that. Start from the definition of e to the x as a power series. 1 plus x squared over 2 factorial plus x cubed over 6, and so on. Differentiate term by term. The series just shifts down by 1 power and lands exactly back on itself. E to the x is, by construction, the one function that reproduces itself under differentiation. Now substitute x equals I omega t and apply the chain rule. The derivative is e to the I omega t times the derivative of I omega t, which is I omega. So, I omega times e to the I omega t. Differentiation is itself multiply by I omega, rotate 90 degrees, and scale by omega. Not by definition, because that's what falls out of the same power series that defines the exponential in the first place. Just as 2D rotation is explained by complex numbers, mathematicians asked, can 3D rotation be explained the same way? The natural first guess, just add a second imaginary axis, x plus I y plus jz. It doesn't work. Multiplying 2 of these triplets leaves a term, the product I times j, with nowhere to go. William Rowan Hamilton spent a decade on this before realizing, in 1843, that the fix needs not 2 but 3 imaginary units, I, j, and k, together with 1 real dimension. A quaternion is a 4-component number, q equals a, plus b times I, plus c times j, plus d times k, where a, b, c, d are ordinary real numbers. Hamilton's single-carved equation determines the entire algebra. I squared equals j squared equals k squared equals I, j, k, equals -1. From that one relation, the full table can be derived. Multiply both sides of I, j, k, equals -1 by I, j, or k in turn. I, j, equals k. J, k, equals I. K, I, equals j. Cyclic order, right-hand rule. J, I, equals -k. K, j, equals -I. I, k, equals -j. Reverse order flips the sign. Going clockwise around I, then j, then k, then back to I, gives a positive product. Going counterclockwise flips the sign. That asymmetry, order determining sign, is precisely why quaternions can represent orientation, something a commutative system cannot. Rotating around x, then y is physically different from rotating around y then x. A quaternion is best read as q equals s plus v vector. A scalar s plus a 3D vector v living along I, j, k. Multiply two pure quaternions, scalar part 0, i.e. ordinary 3D vectors, and something remarkable falls out. U vector times v vector equals -u dot v plus u cross v. The dot product and the cross product, normally introduced as two completely unrelated operations, are both hiding inside a single quaternion multiplication. Worth deriving on screen once, since it's the clearest possible proof the algebra isn't arbitrary. Let U equal B1I plus C1J plus D1K, and V equal B2I plus C2J plus D2K. Multiplying two three-term sums produces 9 pairwise products, written out in full, none skipped, each one converted using the table. Now collect the 9 results by type. The terms with no I, j, or k form the scalar part. The rest sort into 3 groups, by which unit they carry. Scalar, -b1 b2 minus c1 c2 minus d1 d2. That's -u dot v. The I, j, k coefficients. That triple is precisely the textbook cross-product formula for U cross V. Nothing was engineered to make that happen. It's a direct consequence of the multiplication table. Put the scalar and vector parts back together. U vector V vector equals -u dot V plus U cross V. A natural question. The dot and cross products fell out of multiplying two pure quaternions. Does the same structure survive when the quaternions carry a non-zero scalar part too? Let Q1 equal S1 plus U vector, and Q2 equal S2 plus V vector, fully general quaternions. Multiply them out using ordinary distribution, no new rule needed, since scalars commute with everything. Q1 Q2 equals S1 S2 plus S1V plus S2U plus UV. The last term, UV, is exactly the pure quaternion product just derived, substituted in. Q1 Q2 equals S1 S2 minus U dot V plus S1V plus S2U plus U cross V. So yes, the dot and cross product are present in every quaternion multiplication, pure or not. There's simply the UV piece sitting inside the full product. Setting both scalars to 0 recovers the pure case. That's the special case, not a different phenomenon. This general formula is exactly what's silently running inside the rotation sandwich, coming up next, since Q itself is not a pure quaternion. Up to now, the usual way to teach this is, here's Q, here's the sandwich, memorize it. We're not doing that. We're going to try the same instinct that worked in 2D, watch it break, and fix exactly what breaks. Same style of reasoning as Hamilton's own struggle. Try the direct thing, see precisely where it fails, and let the failure tell you the fix. In 2D, rotation was 1 multiplication. P prime equals e to the I theta times p. The tempting guess is that 3D works the same way. Pick some unit quaternion Q and rotate with a single multiplication, V prime equals QV. The next scene will show, concretely, why that guess fails. First, we need a coordinate system suited to the problem. Let U hat be the unit length rotation axis. Any vector V splits uniquely into a piece lying along the axis and a piece perpendicular to it. Here's that rotation, concretely. V sweeping once all the way around the axis. V equals V parallel plus V perpendicular. V parallel equals V dot U hat times U hat. Write K for that scalar, V dot U hat. And V perpendicular is just V minus V parallel. This split is the natural one, because a rotation about U hat should leave V parallel completely alone, since it's sitting on the axis, and should only turn V perpendicular. So any correct rotation formula has to treat these two pieces differently. One more piece of setup. Define W equals U hat cross V perpendicular. That's V perpendicular rotated 90 degrees about the axis, using the ordinary right-hand cross product. W will be the second axis of the rotation, playing exactly the role that IV played for 90-degree rotation earlier on. Try the naive single multiplication with Q equal to cosine phi plus sine phi times U hat for some angle phi. We're writing phi rather than theta for now, since we haven't decided what angle to use yet. Multiply just the axis-aligned piece. V parallel equals K times U hat. Q times V parallel equals cosine phi plus sine phi, U hat, times K times U hat. That equals K cosine phi, U hat, plus K sine phi, U hat squared, which equals negative K sine phi, plus K cosine phi, U hat. We used U hat squared equals -1, since U hat is a unit pure quaternion. Look at that result. It has a non-zero scalar part, negative K sine phi. A single multiplication has pushed a piece of V parallel out of the purely imaginary subspace into the real numbers. Whatever QV represents, it is no longer a pure 3D vector. There's no rotated point, XYZ, that this could be. This is the concrete, computed answer to why we can't just multiply once. A single multiplication provably leaks into the scalar part for any non-zero phi. Multiply on the right by Q inverse, cosine phi minus sine phi U hat, as well, and check whether that cancels the leak. First, the axis-aligned piece. QV parallel times Q inverse equals negative K sine phi plus K cosine phi U hat times cosine phi minus sine phi U hat. Expand the four cross terms. The two scalar terms, negative K sine phi cosine phi, and using U hat squared equals -1, plus K sine phi cosine phi, cancel exactly. The remaining terms are K sine squared phi, U hat, plus K cosine squared phi, U hat, which is just K times U hat. QV parallel Q inverse equals K times U hat equals V parallel. The leak is gone, and the axis-aligned piece is completely unchanged. That's exactly what a rotation about that axis should do to a point sitting on the axis. That's the direct, computed answer to why the sandwich is needed. The second multiplication is not decoration. It's the specific operation that cancels the scalar leak the first multiplication introduces. Now run the perpendicular piece through the same sandwich. QV perpendicular equals cosine phi V perpendicular plus sine phi W. QV perpendicular times Q inverse equals cosine squared phi minus sine squared phi, V perpendicular plus 2 sine phi cosine phi W. That's cosine 2 phi, V perpendicular plus sine 2 phi W. There it is. The perpendicular piece rotates by 2 phi, not phi. This is where the half angle actually comes from. Not an assumption. A consequence of the sandwich doubling the angle. Since we want the true rotation angle to be theta, set 2 phi equal to theta, so phi equals theta over 2. That's the whole origin of the half angle. It's the unique choice that makes the doubled sandwich angle come out to theta. Substitute phi equals theta over 2, and recombine the two pieces. QV Q inverse equals V parallel, plus cosine theta V perpendicular, plus sine theta, times U hat cross V perpendicular. This is exactly the classical Rodriguez rotation formula for rotating a vector by theta about an axis. A formula that predates Hamilton and is normally derived by pure vector geometry arguments. Reaching it here, independently, from quaternion algebra, is a genuine consistency check that nothing in this derivation was arbitrary. Writing u hat as ux, uy, uz, and folding phi equals theta over 2 back into q gives the quaternion this whole section was built to justify. Q equals cosine theta over 2 plus sine theta over 2 times uxi plus uyj plus uzk. And Q inverse equals cosine theta over 2 minus that same vector part. And the point being rotated, v equals x, y, z, must go in as a pure quaternion. V equals xi plus yj plus zk with zero scalar part. And now it's clear why. The entire derivation, the leak canceling to zero, the clean split into v parallel and v perpendicular, only goes through because v started with zero scalar part. We showed earlier that if s isn't zero going in, an extra term appears that this derivation never accounted for, and the clean rotation formula breaks down. A pure quaternion is simply the natural embedding of an ordinary 3D point into quaternion space. The direct 3D analog of embedding the 2D point x, y is the complex number x plus iy, which likewise carries no separate real axis extra quantity. One more consequence falls out for free. Replacing phi with phi plus pi sends cosine phi to negative cosine phi, and sine phi to negative sine phi. That is, q goes to negative q. Here's the direct reason: no angle chasing required. Negative q inverse equals negative q inverse. Inverting flips the sign right back out. So sandwich v between negative q and its inverse. The two minus signs come along for the ride, one from each side. And negative 1 times negative 1 is just 1. The two minus signs cancel exactly. Negative q, v, negative q inverse, equals q, v, q inverse. Algebraically, exactly the same output for any v at all. It also matches the angle picture. The rotation angle in the formula is 2 phi, and 2 times phi plus pi is 2 phi plus 2 pi. The same angle, modulo a full turn. Let's see it. Watch. This sweep is the rotation you get using q. Now reset, and use negative q instead. Same sweep, same destination, exactly as the algebra just guaranteed. Every physical orientation corresponds to exactly 2 unit quaternions. This is called a double cover of the rotation group. This same need to double up, one trip around, isn't enough. You need 2. Is also the structure underlying spin 1/2 particles in quantum mechanics, which need a full 720-degree turn to return to their original state. Wind a belt through 1 full turn, and it stays visibly twisted. Wind it through 2 full turns, and, remarkably, it untwists back to flat. To match the concreteness of the 2D worked example from earlier, here's a full worked 3D rotation. Rotate v equals 1, 0, 0 by 90 degrees about the z-axis. Theta equals 90 degrees. Axis u hat equals 0, 0, 1. Theta over 2 equals 45 degrees. Cosine 45 equals sine 45 equals root 2 over 2. Write it for root 2 over 2. Q equals a plus ak. Q inverse equals a minus ak. V equals I. Step 1. Compute QV. A plus ak times I equals ai plus a times ki equals ai plus aj, since ki equals j. Step 2. Compute that times Q inverse. ai plus aj times a minus ak equals a squared I minus a squared times ik plus a squared j minus a squared times jk. Using ik equals negative j and jk equals I from the table, that's a squared I plus a squared j plus a squared j minus a squared I equals 2 a squared j, with a squared equal to 1/2. This gives v prime equals j equals 0, 1, 0. A 90-degree counterclockwise rotation of 1, 0, 0 about the z-axis should land exactly on 0, 1, 0. Confirmed. Euler angles, roll, pitch, and yaw are intuitive. 3 rings, 3 independent axes to turn. Turn all 3, and each one moves independently. But push pitch toward 90 degrees, nose pointing straight up, and watch the roll ring. At 90 degrees, the roll axis swings all the way around to line up with the yaw axis. Rolling and yawing now do the exact same thing. One rotational freedom has vanished. This is gimbal lock. Quaternions don't have this problem. There's no orientation where they lose a degree of freedom. Let's ground all of this in something concrete. How an aircraft actually tracks its own orientation, in real time, thousands of feet up. Roll, pitch, and yaw. The same 3 axes as before, now attached to a real airframe. Aircraft attitude, meaning orientation, not altitude, is traditionally described with 3 Euler angles: roll, pitch, and yaw, intuitive to pilots. But gimbal lock is a real hazard. As pitch approaches 90 degrees, nose pointing straight up, the roll and yaw axes align, and the representation becomes singular. A small physical rotation can now demand an enormous, unstable jump in the represented angles. This isn't hypothetical. The Apollo 11 guidance computer used a 3 gimbal platform and could genuinely lock up during certain maneuvers, which is where the famous in-mission gimbal lock alarms came from. Flight control and navigation systems instead represent the aircraft's orientation relative to a fixed reference frame, say northeast down, as a single unit quaternion Q. The same Q as before. Rotating any vector between the aircraft's body frame and the Earth frame is exactly the sandwich product. As the aircraft maneuvers, this quaternion updates continuously, a live attitude readout. An aircraft's inertial measurement unit measures angular velocity omega, how fast the aircraft is currently rotating about its own body axis, sampled hundreds of times per second. Rather than quoting the update equation, let's derive it the same way the 2D exponential's derivative was derived earlier, as a small time step limit. Over a tiny interval delta t, the body turns through a tiny angle delta theta, equal to the magnitude of omega, times delta t, about the instantaneous axis, omega hat, equal to omega over its magnitude. That small rotation is exactly represented by delta q equals cosine delta theta over 2, plus sine delta theta over 2, times omega hat. For small delta theta, cosine delta theta over 2 is approximately 1, and sine delta theta over 2 is approximately delta theta over 2. The same small angle move used implicitly whenever a derivative is taken as a limit. Substituting delta theta equals magnitude of omega times delta t. Delta q is approximately 1 plus delta t over 2 times omega. Writing omega now for the pure quaternion: 0, omega x, omega y, omega z. Composing this small extra rotation with the current attitude, q of t plus delta t, approximately equals q of t, composed with delta q, which gives q of t plus delta t, approximately equals q of t plus delta t over 2, times q of t, times omega. Rearrange, and take delta t to 0, forming the derivative directly from its definition. Q dot equals 1/2 times q times omega. That's the quaternion kinematic equation, arrived at the exact same way the 2D exponential's derivative was. Rate of change of orientation equals current orientation multiplied by angular velocity. 1 in 2D with a scalar omega, 1 in 3D with a vector omega. Integrating this forward in time is exactly how flight computers track attitude between GPS or star tracker fixes. In practice, gyroscope measurements drift over time. Modern autopilots fuse gyroscope-integrated quaternions with accelerometer and magnetometer, or GPS-derived heading and readings, typically via a quaternion-based complementary filter or an extended Kalman filter. This keeps the attitude estimate both smooth from the gyroscope and drift-free, anchored by the other sensors. This pipeline is exactly why quaternions, not Euler angles, are the internal attitude representation in autopilots, drone flight controllers, and spacecraft attitude control systems. Let's put it all side by side. Algebraic form, a plus bi versus a plus bi plus cj plus dk. Point encoding, p equals x plus iy versus v equals xi plus yj plus ck. Rotor form, e to the I theta equals cosine theta plus I sine theta versus q equals cosine theta over 2 plus u hat sine theta over 2. Operation, p prime equals e to the I theta times p versus v prime equals q, v, q inverse. Degrees of freedom, one angle versus axis plus angle under a unit length constraint. Key advantage, simpler than matrices versus avoids gimbal lock and enables smooth slurp interpolation. Same idea, one dimension up. A number that rotates things, built from the requirement that lengths multiply correctly. And in 3D, that requirement costs you commutativity and buys you an entire extra dimension.